Right-angled triangles and trigonometry have numerous applications in various fields including mathematics, physics, engineering, and even art and architecture. But did you know that the concept, first described by an ancient Indian mathematician, Baudhayana, popularly known as the Pythagoras theorem, which we often associate with geometry and trigonometry, has a fascinating connection to how well we see? Let's explore this surprising relationship with Baudhayana, Pythagoras, right-angled triangles, trigonometry, Snellen, and visual acuity. Namaskaram, I am Dr. Biju Raju. I am consultant vitreoretinal and cataract surgeon at Dr. NSG Raju's Eye Hospital, Kochi, India. Thank you for visiting my channel, and if you like it, please share and subscribe to my channel. The ancient Egyptians used ratios of similar triangles to construct their pyramids, and the Babylonians used trigonometric functions to describe arc lengths and chords. The Egyptians and the Babylonians were the first to use ideas of trigonometric concepts. Pythagoras was a Greek philosopher and mathematician who lived in the 16th century BC. He is best known for the Pythagoras theorem or the Pythagorean theorem, which states that in a right-angled triangle, the square of the hypotenuse, that is the side opposite the right angle, is equal to the sum of the squares of the other two sides. A square plus B square equals C square. This theorem connects algebra and geometry. The statement A square plus B square equals C square, that is an algebraic statement, but the figure that it comes from is a geometric one. Now, why is that? Trigonometry and the Pythagorean theorem are closely related because both involve the study of relationships in triangle, particularly right-angled triangles. The Pythagorean theorem provides a foundation for defining the trigonometric ratios that underpin the structure of right-angled triangles. Many basic trigonometric identities are nothing more than Pythagoras' theorem. In India, a great mathematician, Baudhayana, lived in 800 BC, approximately 1000 years before Pythagoras was born. It is said that Baudhayana was the first to mention the relationship of the right-angled triangle. Baudhayana was a Vedic Brahmin priest and a great architect. He wrote one of the earliest books in mathematics, Sulbasutra, to provide rules for making altars for religious rites. Therefore, the original discoverer of the concept of the present-day Pythagorean theorem should rightfully be the great Indian mathematician Baudhayana. Nevertheless, we continue to use Pythagoras theorem or Pythagorean theorem for concepts discovered by Baudhayana. From the right-angled triangle, we derive the trigonometric ratios. Using the trigonometric ratios, one can find either the length of a side of the triangle or the angles of the triangle. So what are these trigonometric ratios? Trigonometric ratios are mathematical relationships between the length of the side of a right-angled triangle and its angles. These ratios form the foundation of trigonometry and are used to solve problems involving triangles and periodic phenomena like waves and oscillations. As we saw, in a right-angled triangle, the hypotenuse is the longest side, and that is opposite the right angle of the triangle. And if you consider this angle as theta, then the adjacent side is the side next to the angle of interest, that in this case theta, and the side opposite to angle theta is the opposite side. The trigonometric functions include sine, cosine and tangent and the reciprocals. And sine theta is the ratio of the opposite side by hypotenuse, and cos theta is the adjacent side by the hypotenuse, and tan theta opposite side by adjacent side. And the mnemonic for this is SOHCAHTOA. SOH for opposite hypotenuse, CAH cosine for adjacent hypotenuse, and tan, TOA, opposite side by adjacent side equals tan theta. And this is something we should remember because we are going to need this as we go along. That is, tan theta equals opposite side by adjacent side. Now for the million-dollar question. How are all these related to visual acuity? Visual acuity is determined by the smallest retinal image, the form of which can be appreciated. And it is measured by the smallest object that can be seen at a certain distance. If two separate points are to be distinguished as separate, they should stimulate two separate cones in the retina, while the one between them remains unstimulated. As in this picture, you can see two cones are being stimulated, but the one in the middle is not. If that happens, then we can distinguish these 2 points as separate. We know that the cone diameter at the macular area, or the average cone diameter in the macular region, is 4 microns or 0.004 millimeters. And thus, this represents the distance between the 2 cones. Therefore, the normal eye should be able to distinguish an image of this size, that is 0.004 millimeters. The smallest size of an image that can be appreciated by the human eye. There are 2 factors that determine the image size on the retina. One is the size of the object and how far the object is placed from the eye. The concept of visual angle easily combines these 2 factors and therefore is the best way to determine the image size on the retina. Here, the image formed by the blue object is smaller than the one formed by the red, though they are both similar in size. The visual angle formed by the blue object is smaller than the one formed by the red because the blue object is farther away from the eye. When we closely observe the path of light from the nodal point to the retina, we see that it forms a right-angled triangle. According to Pythagoras, the size or height of the image forms the base of this right-angled triangle, denoted by the letter H. The distance from the nodal point to the retina, the perpendicular, and the side opposite to the right angle, the hypotenuse. We know that the minimum distinguishable size of an image is equal to the average cone diameter of the macular cone, that is 0.004 millimeters. Therefore, H is equal to 0.004 millimeter. That will be the minimum distinguishable size of the image on the retina. The distance from the nodal point to the retina, that is F, in this diagram is approximately 17 millimeters in a normal eye. From the trigonometric ratio, we now can find the value of the visual angle theta for the minimum distinguishable size of an image on the retina. We know that tan theta equals opposite side by adjacent side. Remember SOHCAHTOA. So here, for angle theta, H is the opposite side, which is the smallest image size that can be perceived, and F is the adjacent side, which is the distance from the nodal point to the retina. So tan theta equals H by F, and therefore H is equal to F into tan theta. For small angles, tan theta can be taken as the same value of the angle, that is theta. So therefore H equals F into theta. We substitute the values. 0.004 is equal to 17 into theta, and therefore theta is 0.004 divided by 17, that is the size of the smallest image that can be perceived by the human retina divided by the distance from the nodal point to the retina, and that gives us the value of 0.000235 radians, which is approximately equal to 1 minute of an arc, or 1 arc minute, or simply put 1 minute. This is because a visual angle of 1 minute is approximately equal to 0.000291 radians. Thus, to produce an image of minimum size of 0.004 mm, the object should subtend a visual angle of 1 minute, and this is taken as a standard of visual acuity, or the minimum angle of resolution. Fast forward to 1862. Enter Dr. Herman Snellen, a Dutch ophthalmologist who used these concepts to design the chart for standardized testing of visual acuity. The most significant innovation was Snellen's use of what he called optotypes, specially designed characters generated on a 5x5 grid rather than using standard fonts. The chart he created, the Snellen chart, has stood the test of time and is still the most popular vision chart used for testing visual acuity. He designed the optotypes based on the concept of minimum angle of visual acuity, which we now know is 1 minute. Let us design the optotype as Dr. Snellen wanted it to be. Draw a 5x5 square, and now we divide the square into smaller 1x1 squares. Now we draw each line of the letter within the 1 minute square. Dr. Herman Snellen designed the optotypes so that each letter is of such a shape that it can be enclosed in a square 5 times the thickness of the lines composing the letter. The breadth of the lines of the letter, that is the size of the smaller squares, is such that their edges subtend a visual angle of 1 minute when they are at a specific distance. Therefore, each letter subtends an angle of 5 minutes of an arc at a specific distance. But to analyze its form completely, that is, to see the constituent parts that form the letter, the eye must be able to resolve them to a standard limit of 1 minute, the smaller 1x1 squares in our example. The size of the optotypes can also be calculated from the same trigonometric ratio, tan theta equals opposite side by adjacent side. Here, in this diagram, h is the size of the optotype in millimeters, d is the distance in meters, and theta is 1 arc minute or 1 minute. As we know, it is the minimum angle of resolution. Now let's calculate the size of the first optotype, which can be read by a person with normal visual acuity from a distance of 60 meters. This means that this letter size will subtend an angle of 5 minutes with its constituent parts subtending 1 minute at a distance of 60 meters. From tan theta equals opposite side by adjacent side, we now know that it is h by d and h by 60, and here h is the size of the optotype we have to determine. As discussed before, tan theta is almost equal to theta for small angles. So theta equals h by 60. A visual angle of 1 minute is approximately equal to 0.00291 radians. We discussed that earlier. So 5 minutes of an arc is 5 into 0.00029 radians, which is equal to 0.00145 radians. So h equals 0.0145 into 60, that is 0.087 meters or 88 millimeters. Thus, the size of the first optotype is approximately 88 millimeters. So, an angle of 5 minutes is formed at a distance of 60 meters. The second optotype will form an angle of 5 minutes at 36 meters, the third at 24, the fourth at 18, the fifth at 12 meters, the sixth at 9 meters, and the seventh optotype will form an angle of 5 minutes at 6 meters. Now 6 by 60 is the vision of that person who from 6 meters can read only the 88 optotype. A person with normal vision would read the same optotype at 60 meters. In that sense, visual acuity of 6 by 60 is subnormal. With normal visual acuity, he should have read the 7th line on the Snellen's chart, the optotype which subtends 5 minutes of an arc at 6 meters. That visual acuity, which we term as normal, is 6 by 6. As seen, the 6 in 6 by 60 is the distance at which the chart is viewed, and 60 is the optotype seen clearly by the person with a normal visual acuity viewing it at 60 meters, the distance at which the entire letter subtends 5 minutes of an arc on the retina. The works and ideas of Baudhayana, Pythagoras, and Dr. Snellen, those separated by centuries, converge like tributaries of a river cascading over the cliff of human imagination into a breathtaking waterfall of unique applications. I find it really fascinating that several minds working at different timelines in history on concepts that look totally unrelated, and yet finally they all converge at some point of time to make sense of all the chaos. And somehow that we are all connected. We just have to figure out how to connect the dots. Thank you.